So just a reminder, hopefully this is not a surprise, but there is your first test is this Friday morning. It sounds like someone can't hear me. Can you all hear me?
Okay. Can.
All right, good.
It's Friday
so
morning.
First test is this Friday morning, isn't it?
You did not say anything about that.
Okay. Stay posted then. I think it's
It wasn't an announcement.
Okay. What he has done in the past, and I don't remember what time the announcement said, but what he's done in the past is you have like a 2-hour window to start. And then there's a time limit on the test itself that starts when you start it, but I think you have a little bit of flexibility as to when you begin it. But yeah, I'm sure he'll give more details about that on Wednesday.
So you don't know if, oh, sorry.
Go ahead.
You don't know if the test will be in person or strictly through Canvas?
If it's anything like it was last semester, none of you will show up in person. But I'm not going to promise you anything. I'll just tell you that last year, the test was done entirely online. It's proctored remotely. Yeah, you won't actually. If it's your turn to show up, don't show up unless you hear differently.
Does that mean it's going to be a lockdown browser, or is this going to be something else? Or
so last semester was lockdown browser. I'm imagining something similar. All right, I am going to go ahead and share my screen. It looks like almost all of you are here now. If you don't already have available, please get some paper out. Be ready to take some notes. I'm already recording. So let's do this. I am showing you this trapezoidal looking solid here. And I want you to draw 3 things for me. Everything we've been doing lately in the last, this week at least, has been finding volumes of solids we create by revolving around an axis. So I have a 2-dimensional region here, and we're going to create 3 different solids by revolving around the left edge, the top edge, and the bottom edge. So I'm going to give you a few minutes to get started on that. Let you guys think about it first, and then I'll show you my sketches. So I have 12:03. I'll give you 3 or 4 minutes here.
It's okay if I ask a quick question. It's not related to recitation, but
Go for it, Mark.
so I was just wondering what the tests I usually like what kind of questions are they composed of? Is it mostly math or is it mostly conceptual?
Yes, I mean the conceptual questions that you'll have to deal with, you know, they may not be what you're used to when you think of you know, how you've been shown math in the past, but you know, that is what math is. So yeah, I mean I think based on, you know, how Mark has been presenting this stuff and how you've been expected to understand it, yeah, definitely expect some a heavy amount of conceptual questions tomorrow.
So you would agree that most of the questions on a quiz are based on the test are based off of the daily quizzes we take at the end of each class.
Those are definitely a good thing to go back and look at. As long as we're talking about what I really think you're after is how you should prepare. Am I right? Well, I think it's good to have a plan of attack anyway. I think looking through some of the old lectures, I don't know if I would start there. I mean, there's a lot of old lectures to watch. But I think there's an exam prep area in the modules on Canvas that I think would be good to look at first. There's a couple worksheets in there that if there are not solutions in there yet, they will be there soon. There are, I would start there. And I feel like the biggest thing that I see on the homeworks that I make comments about is like a lack of completeness when you're explaining something. For example, the volume homework assignment that you just turned in, the GC activity. I think one of the questions was, you know, when X has gone from 0 to halfway through the interval, is that half the total volume? And I got a lot of answers to the effect of, well, no, it's not, because when I multiply this by 2, I don't get the same volume, which isn't really an explanation. Essentially, I mean, all you're saying is like, well, it's not. But yeah, I understand that it's not, and I think it's easy to recognize that that volume is not half of the total volume, but we're looking for reasons why. So the people who are on the right track are the ones who said something about, you know, the rate of change of radius is increasing for the entire over the entire X interval, or saying something about the geometry of that solid. So basically there is more volume between X equals pi over 2 and X equals pi than there is between X equals 0 and X equals pi over 2. So the biggest thing I can hit on, and I don't think this will be a surprise to anybody after 4 weeks of this, is it's not enough to be able to, you know, quote unquote get to the right answer, or to make the right calculations, or to mimic the steps that you have seen. You have to know why you're doing those things. You know, based on what we're doing lately, if you're trying to find a volume, you know, it's not enough to know that you need to integrate the area of a circle. You gotta know why am I integrating the area of a circle and not the area of a rectangle? And that's basically what we're gonna be talking about today. So let me go ahead and stop sharing here. And I'm gonna share from my iPad now, so I can actually draw well.
Can I ask one more question about the test?
Go ahead, Hannah.
Is he gonna by chance release like the quizzes that we've been taking all semester so we can like study those?
I don't know if he is, but I'll answer that 2 ways. You can definitely ask. So I would encourage sending an email to him to see if he'd be willing to do that. Or Michael is saying that he thinks he has. I would go check that out. Preferably
Okay.
not right now, but I can't stop you, obviously. You can go check that out. Or if he has not released them, you can definitely make an appointment with one of us between now and Friday. Michael is saying he's been able to see past questions, so. All right, I got a confirmation, so.
Perfect.
Hopefully that's true for everyone. But if you look over the quizzes and this is for anybody, if you have anything you want to talk about between now and Friday, I do not have office hours other than Monday between 10 and 1, but I'm totally willing to talk with you over email or to make appointments, things like that. I've said it before. I'll probably keep saying it. Feel free to reach out to me. I will definitely help however I can. All right, let's go ahead and get started. So these first three here, we're going to revolve this trapezoid region around 3 different edges. So this left edge, so I'm just going to bold in this edge here. And basically, let's start here. Let's start by reflecting this 2-dimensional shape over this line. So it should look something sort of like this. And then as we revolve it around that vertical line, you're going to get a shape like this. Kind of like a Reese's peanut butter cup type shape. Hopefully you had something similar. Any questions about that first one?
I
Alright.
have a question.
Go for it.
I kind of spaced out the other side of it. Is that okay?
You mean the left side, or what do you mean by the other side?
The left side.
Yeah, so when you revolve around an axis, so I think most of the things we've done and most of the things you'll see are around the x-axis or the y-axis. And then in this case, this, you know, I bolded it in where it intersected my graph, but let me do a dashed line there. Really, that dashed line is where I'm rotating the shape. So if you have some area on the right, which we do, it's like where I'm kind of scribbling in here, then as you revolve around that left edge, you're going to get that area is going to it's going to revolve to the left as well.
Okay, I get it now. Thank you.
Yeah. No problem. Yeah, it's something to keep an eye on. And we're not going to do calculations with all 3 of these shapes, but it's really good to kind of know what they're going to look like, because with this stuff, and many of you have probably already realized it, you have very little chance of kind of visualizing and understanding where to go next if you can't see it. So I think drawing pictures is always a good idea. So in purple this time, we're going to revolve around the top edge. So just to be consistent, I'll make a dashed line that extends the entire, basically that infinitely long horizontal line there. And now I want to take this area and revolve that. Basically, I'm going to revolve it upward around that axis. So first thing I'll do is just reflect that shape as well as I can. And then try to show that we're going to have a cylindrical arrangement on the left there. How do you feel about that one there? All right. Let's choose red then for the last one. So revolving around the bottom edge, and this is the one we're going to deal with for pretty much the rest of this period. So here's the edge we're worried about. So first things, I think a good way to start drawing these regions or drawing these solids is just to by basically mirroring it over whatever the line is. So basically just trying to recreate it in 2 dimensions first, and then revolving around here. And I really want to pause here because, like I said, we're going to be doing a lot of things with this specific shape for the next half an hour or so.
And just to be clear, this one has a funnel kind of notch taken out of the right side.
Yeah, so, and I guess that's one thing I'll bring up here. If I were to, so this hole kind of taken out of this right-hand side here, that's a cone shaped hole. So as you revolve that triangle around the x-axis, you're going to get that kind of a missing cone there. Any questions so far? All right, like I said, we're going to be doing quite a lot with this shape. Now I want to find the volume of this shape in two different ways. So first, we're going to vary through the x-axis, and we're going to be revolving around. So what line did we just revolve this thing around to make that red solid there?
X-axis.
That's the x-axis, right? Let's try to make them coincide. But yeah, I want my x-axis to be my axis of rotation. That's fine. Leave it like that.
Y equals 0.
Y equals 0, x-axis. So let me try to recreate this drawing one more time. And the first thing we're going to do is use delta x intervals. So shade in this area. Actually, I want to not shade it in. I just want to shade in an elementary strip of this rectangle. And remember, we, for this part, are varying through x. So I want my independent variable to be x. And I'm letting I got my empty shell here. So first thing I will ask you is this. So I have this empty shell. I have this one strip here. I'll go ahead and revolve this one strip around the x-axis. What shape is this strip? After I revolve that strip there, what shape did I just make?
Circle.
Close. It's a cylinder, right? So yeah, I mean, a cylinder has the two circular faces, but really when I'm in when I make that rectangle right there, rectangle is a two-dimensional object. But when I revolve that around the x-axis, I have generated a three-dimensional object. So yes, it has circular faces, but I've made a three-dimensional shape, specifically a cylinder in this case. So next question. And one thing I'll remind you is, actually, you guys remind me. How do I find the volume of a cylinder?
Pi r squared h.
Pi r squared h. So really, this is the
That's
volume
only
we're finding.
that's only for a circular cylinder, right? It's really the area of the base times the height.
I think you're thinking of a prism. By definition, a cylinder is circular.
Okay.
A prism can be any shape. All right, so we have the volume of a cylinder being, pi r squared h. But now what we want to find out is this. We want to find, and I'll represent it two different ways. An area, or I think what Mark prefers is rate of change of volume. And one thing I want to point out is this. The rate of change of a volume is always an area. Always, always. But we have to figure out which area that's going to be. So as we are varying to the right, here's our cylinder, like kind of our vertical up and down cylinder here. As we vary to the right, we're basically adding little, like really thin sheets, really thin areas onto this cylinder to give it more volume. So as x changes, as x gets bigger, are we adding those sheets to the base, the flat circular base, or are we adding those sheets to the kind of the outside, the lateral surface?
Outside.
Jose, go again. I didn't quite hear you.
The outside.
Outside.
As we vary through x, Maybe I'm confused what you mean by outside. Is that the curved surface or the flat surface?
The height of the cylinder.
It's the height of the cylinder, right? So yeah, that's the height. Basically, it's kind of weird to think of a cylinder like this, but really the height is, these cylinders are laid down horizontally. So the height is a horizontal concept in this case. Right, so we are absolutely, as x changes, we are also changing the height. That means we're adding things onto the base. What's the shape of the base in this case here?
A circle.
Circle. So we want to, basically our rate of change is going to be the area of a circle, which is going to be pi r squared.
We're stacking a whole bunch of really thin pancakes.
Basically, yeah. You're stacking thin circles onto the right there. So what we have now is this. Now we're going to use an integral to find this volume, and we know that it's based on this idea. The area or the rate of change of volume is equal to pi r squared. And let's make it a little more general here. Let's do pi times capital R squared minus pi times lowercase r squared. Because in many cases, you're going to have an outer radius, you're going to have an inner radius, and they're going to be different. So we're revolving around the x-axis. What is my outer radius for this cylinder that I'm going to be drawing? Jillian says 2. That's a constant.
Whatever that y coordinate is, which.
Oh yeah, and I forgot to emphasize this. I didn't show you this before, but these are the functions that are bounding the region. So straight line y equals 2x, straight line y equals 2, oh sorry, horizontal line y equals 2, y equals 0, the x-axis, and a vertical line at x equals -3. So yeah, Jillian, you're exactly right. The outer radius is going to be a constant 2. What is the inner radius going to be?
Wait, how do you know the radius is 2?
That's a good question. How do we know that the outer radius is 2? Who wants to handle that?
Because we swept it around that top line, which is 2 units away from the x-axis. So we took the whole thing and revolved it around like this, drew a circle that's 2 units in radius.
Right. And it's worth noticing, for those of you who haven't already, the outer radius on this shape is a constant. That's why it's just 2. There's no function. Basically, your outer radius is, by definition, the furthest away you are from wherever your axis of rotation is. So basically, what's the furthest distance that I'm going to be from the x-axis? In this case, that's just a constant horizontal line of 2. All right. So what is our inner radius going to be?
0.
I have 1 vote for 0.
The reason why I say 0 is because it's right on the x-axis.
Okay, so Mark says we have no inner radius. How do we
For
feel about that?
half of it.
For half of it, right? And that's where we're going to have a little bit of a complication here.
I'd
So-
say the y coordinate.
The y coordinate of what?
Of from the x-axis.
Okay. So Mark is saying that is 0. Ben has followed up and said that is only 0 some of the time.
Oh, so that's the part where we might have to do piecewise function?
Yeah, and that's exactly right. So let's kind of split this up. We know that this is true. So no matter what, this area of a circle is what we're looking at. Can we still say the outer radius is 2 in this other situation? Hopefully we're okay with that. I mean, that outer radius isn't changing.
For part of the second half, yes.
Okay.
Well, the
Except for
outer
part of the
radius,
second half?
outer radius is never changing.
Yeah, the outer radius is just 2 all the time. So this this line right here, I mean, once you get past this point, we're done. There's no more volume to think about.
And just so you know, you made a typo error on the right where you forgot to put a pi next to lowercase r.
Pi next to lowercase r. Oh, thank you. Thank you for that. All right, so on this other side, the inner radius, what would the inner radius be? In fact, let me draw another strip here to show that I don't really have a cylinder this time. I have a cylinder with a hole drilled out of it. All right, so what is the inner radius going to be? Basically, how am I going to tell where the inside of that cylinder is for any x value?
Would it be 2 minus 2x?
2 minus 2x, let's see. How do we feel about inner radius 2 minus 2x?
Where is that extra 2 coming from?
So,
Or the 2 minus, why?
so
but
one thing
if we're assuming, but it's just the inner radius that we're looking for. It's just the y coordinate of that slope.
Okay, so let's talk about this because I think it's I'm really glad that came up actually. So as x goes to the right, hopefully it's clear that as x goes to the right, this inner radius is getting larger. So that's one thing to keep in mind there. As x goes to the right, this distance from the axis of rotation to that rectangle is getting bigger. So that says to me that we need an increasing function of some kind.
This is just a something I noticed, but if you revolve that shape around the x-axis, you kind of also get to see that looks like it's probably like a cone that has been taken out.
Yep.
So basically, what you could do is you could essentially find the volume of the cylinder as a whole, then subtract that cone out.
Yeah, if we were going to do this geometrically, that would also be a way to go. I want to focus on the integral, but you're absolutely right. That is how those will work. And I believe where this 2 minus 2x came from is this. 2 minus 2x, I believe, would give you an exact value for how tall that rectangle is. But that is not what the radius is. If I can give you an example here, let's say I have a circle, and another circle in the middle of it. If I wanted to find this area of the outside, like this donut, let's say the outer radius is 5 and the inner radius is 3. Are we okay with this being the area pi times 5 minus 3 squared?
No,
Hopefully you're
'cause
not
that
okay
would-
with it.
It would just give you the area when it's at a radius of 2, not the
Right.
difference.
So this thing bad, this thing good. So when you're trying to find the area of a circle with another circle removed from it, you really do need to find the area of both circles and then just take their difference. Which is why we can't just purely take, 2 minus 2x. We need to treat this as an outer radius of 2 and an inner radius of 2x. Any questions on that?
How is it little r2x instead of just x?
Because the equation of the line is 2x.
So 2x is what you're saying is that 2x is what is represented by the slant to the side of the shape.
Yeah, by that diagonal line. So one thing I did not say that I probably should have is it clear that the radius in this situation is going to come from y values? So just to kind of reiterate, the outer radius is purely y equals 2. The inner radius, right here where I'm circling, that's y equals something else, right? Y equals something that's varying. And to get what that y equals, you'll have to get, you have to look at the 4 functions I gave you for how this region is being bounded. Let me ask you this, just because I feel like I've seen this a few times. Would it be okay if I just called that r equals y? Could I go to an integral with calling this r equals y?
Yeah, depends on the context.
How about this context? Based on
No.
how I've made these shapes, how I built these cylinders, could I
'Cause
do this?
there's multiple Y's there.
There are multiple y's, that's true, but why else could I not use a y?
Because you're building this as a function of x.
Right, so I am using delta x intervals, right? Which means all of these need to be in terms of x. So I do not want to leave this as y. I want to be explicit and call that 2x. Jillian says, don't both radii rely on y equals 0? They do, Jillian, and that's why, you know, this is one of the way that Mark usually asks this question is our radius a large variation in y, or is it just equal to y?
Okay.
So in this case, the radius is equal to y, which is equal to 2. Kind of scrunched in there. So in this case, the way that Mark asked that question, yes, the radius is just equal to the y value. Because this is y equals 2, this is y equals 0, 2 minus 0 is 2. But in this case over here, since we have that gap between the x-axis and the inner radius there, you have to think about 2 different radii, and in this case, they're both just going to be y values. Up here, I have y equals 2, and in here, I have y equals 2x. But in this case, since they're we're going from y equals 0, they're just going to be equal to y values. All right, you're welcome, and let's go ahead and look at the integral now. So really, let's just start by building the rate of change function. We have said it's going to be piecewise. So let's do this first. What are the x values that are going to govern each? So what x values am I going to be in for the first half of this shape?
-3 and 0.
-3 and 0. How about the other side? I'll give you the 0 for free. Where does it end?
One
2.
moment. So -3, 0. So it's at 2. Wait, I want to say 2.
How do you say 2?
Wait a minute.
This point right here?
Because y equals 2.
Y equals 2, yes, but we do not want this function we're building is an x, right?
Yeah.
So how do we find that x value where that point is?
What is x when those 2 equations intersect?
What are those 2 equations?
Y equals 2x and y equals 2.
Right, so if I want y equals 2x, y equals 2, I can put those equal to each other, and I get x equals 1. So that is going to be the end of our integral here. So now let's actually define the functions in these branches. For the first part of the interval, what's my rate of change going to be?
It's just the area of that circle.
Which is?
pi times the radius squared, and the radius is 2, so 4 pi.
I'm gonna leave it like this just to be really explicit about where it came from. But yeah, the first one's constant. It's gonna be pi times 2 squared. How about in the second part of this?
So the second one, I would say pi times 2x squared.
All right, how do we feel about that?
I disagree.
Okay, what do you have, Jose?
Pi 2 squared minus pi 2x squared.
And one thing I want to point out here is remember your area, your rate of change is always whatever you decided these things were, right? And just to be really explicit, I'll do this. There was no inner radius for that first case. So I'm going to leave it like that, unsimplified, but I think it's valuable to see where everything came from.
And one thing that I noticed on the iMath AS assignment was sometimes in those functions, the pi was factored out. So it was pi times 2 squared minus 2x squared.
Okay, and that's totally valid. You could do that too.
Yeah, it threw me for a loop until I figured out what was going on.
And you'll see that often. So now we have the rate of change of volume. So how would I find a function for the volume itself?
Just add dx or dt, something like that in the end.
Okay, I heard add dx.
Like
That's part of it,
integral-
yes.
Yeah, integral like -3 to x, and just the rate of change, and dx or dt.
Okay, here's what I believe Edward said. The integral over that rate of change from -3 to x. Alondra is asking if we would have to use 2 integrals. I believe we would not in this case. So what's important is we use the piecewise function for our rate of change. So when you're defining the integral like this, that integral is also going to be based on that piecewise function. So there isn't really a need to break up the integral again.
Would we have to add the volume at x equals 0 as well? Or
Why do I not have to add the volume at x equals 0?
is it just because it's 0? Or
It's not going to be 0. So look at my integral. Where is my integral beginning? What's my initial value of x?
-3.
-3. So that is really where volume is going to start accumulating. So if I were to do v sub 0, this would be a positive number because I've already accumulated some stuff. So basically what v of 0 is going to give you is the integral from -3 to 0 of r sub v of t dt, which is going to be something positive.
In this case, it's the part of that thing that's just a tin can type cylinder. Without
Yeah, it's the part that's just the cylinder.
okay, so like we don't add the volume, like the initial volume. It's like I'm just thinking back to like I think it was total accumulation of volume, and we had to add the volume at the initial.
So let's say we accounted for that initial volume here. What would my volume be at x equals -3?
0.
0. So yeah, I've had no area. I've had no like geometry to revolve around the x-axis yet. So this term right here, I mean, you can definitely include it, but just understand it's going to be equal to 0 in that case.
Of course, if we were going to write it not in function notation, but write it out, then we need to add the 2 integrals together, right?
Yeah. But GC can handle this, man. If you were going to do this in GC, it can handle that piecewise function just fine. If you were going to do this by hand, yeah, I would do it in parts. All right, so let's do, and I think, correct me if I'm wrong, but I don't think you've looked at a piecewise function before in this context.
I don't think so.
Okay, so let's move on to the Y case. So again, Let's recreate the shape.
And there are at least a couple of them on the assignment that's due tonight.
I thought the AS was due tomorrow night.
Tomorrow night.
Yeah, I think that's probably the biggest reason that he pushed it back. So here's the region. Again, so even though we're going to use y as the variable now, I still want the same shape. We're still going to wrap this around the x-axis, except now I'm going to have a rectangular strip that looks like this. And revolve this around the x-axis. All right. So pretend that's symmetrical, and let's try to figure out how to find the rate of change here. So one thing I really want to emphasize that remains constant all the time is that the volume of a cylinder is pi r squared h. And just to kind of bring all this home, when we define this integral like this, r sub v of t was the area of a circle, right? Pi r squared. What is dt doing? What does that represent?
The height.
That's the height. So that dt is the little infinitesimally small change in height for each interval. So no matter what, when you're integrating, you are adding up volumes of cylinders. So that will always be true. So volume equals pi r squared h. Now let's think about the cylinder I drew here, which I can already tell I did not do correctly. Should be above. So if I do a cylinder like this, revolving around the x-axis, now our independent variable is y. As y varies, what dimension is changing, the height or the radius?
Radius?
This time it's the radius. So because it's the radius, we're going to find an area or the rate of change of volume again. Basically, this is kind of like the analogy he used in class yesterday. You're wrapping the toilet paper, or you're putting the paper towels back on the roll, like little thin sheets. But what shape is that? Like, what kind of area are you adding? What geometric shape? Ben's shown me a square or hopefully something a little more, rectangle. And basically that's what you're doing. You know, if you can imagine like kind of unspooling, a toilet paper roll is obviously a cylinder, but when you take some off, you're taking off a rectangle. So how do I find the area of that rectangle in this situation? So here's a cylinder. Radius, height. Hopefully you can see that one of the dimensions of that rectangle will be the height. If I were to peel this off, what would this dimension be? Or what would it be equal to?
2h?
Pi RH.
I heard pi RH, I heard 2h.
2 power H.
No H yet.
No h yet. So I mean, the height is one dimension here, but the other dimension, hopefully you can see that would be the circumference of this circle here. And the way we find a circumference is by 2 times pi times radius. So like I said before, the rate of change of volume is always an area. In this case, the area is going to be a rectangle. Last case, it was the area of a circle. So now what we have to do is this. We have to find this function here. The rate of change is going to be 2 times pi times r times h. So our job now is to figure out what the radius is and to figure out what the height is. So if we look at our shape here, for any given interval, what is my radius going to be?
Would it be 2?
Not quite, because remember my My independent variable is y. So I need all the radii between 0 and 2. So it's definitely variable.
So basically, it's y value with respect to x.
So I heard y, but we want to get this in respect of x. So remember, I am using y as my independent variable. So is r equals y okay?
Yeah, we already have y.
Yeah, we want everything in terms of y. So we're done with radius. Now the height. Here's the height of our, our one example strip we have here. How tall is this cylinder going to be? So, and I guess I should go back to Mark Ashbrook's question here. Is this going to be related to, so it's obviously horizontal. So it's something having to do with X. But is it going to be purely the X value, or is it going to be some other variation in X? And while you're thinking about that, I'm going to draw another rectangle in here to show that, yes, they change in height. So this height, if we can find, basically this height is basically a difference between these 2 points here. How would I find the value of this left, basically the left end of any cylinder?
The value of x at that
Okay.
point.
Oh, sorry. What is the value of X over here?
-3.
Always?
On the left end. Yeah.
Yeah, so on the left end, the value is always -3. How about the right end? Pretty obviously that, this right end location changes. So how would I find that right end?
Y over 2.
I heard y over 2. Where did that come from?
The equation you gave us, like above.
Yep, there you go. So for now, I'm just going to do this. I'm going to call this x plus 3. We okay with that? Maybe I'll make this a little more explicit. X minus -3 simplifies to x plus 3. But x is not okay because I want to have this whole thing written in terms of y. So this x value right here is related to this equation, y equals 2x, which if I solve for y, I get x equals y over 2. Now we're almost done. I'm going to write this rate of change of volume as a function of y to be 2 times pi times y times y over 2 plus 3. Any questions on that? All right, take us home. How are we going to find the volume then?
So basically, integral from 0 to 2, I guess. To x to y, I mean.
There you go.
And rate of change dt.
There you go. Any questions on either one of these?
Did you get the +3 in the x plus 3 from the difference from the end to the point where it starts to change?
Yeah, absolutely. So basically what's going on here is this. Call this my final value. Call this my initial value. And yeah, basically taking the difference of those two things gives you the pure height for any one of those rectangles I was going to draw.
Okay, gotcha. Thank you.
No problem.
Why is the integral from y to 0?
That's a good question. Why is the integral from 0 to y actually. Why does the integral go from 0 to y? In the first example, my integral started at -3. So why is it 0 this time?
So basically, you are changing from y-axis. You are not changing from x-axis. So you start at y equals 0. So that's why y equals 0, I guess.
Okay, that makes sense.
Yep. So yeah, always keep in mind what your independent variables are. Yeah, so in the first example, I was accumulating volume starting from x equals -3. In this next example, I was accumulating volume starting at y equals 0.
You could rewrite this to start at anywhere, but you start to confuse yourself if you're not careful about it.
Yeah, but I want to start at the logical beginning. Any more questions before I stop sharing and let you all go?
So we don't care about volume accumulated underneath of the x-axis?
Well, we're still going to get that because, so our region was entirely above the x-axis, right?
Right.
But when we revolve it, so one thing, I think I can explain it this way. Let me just get rid of one of these rectangles here. So this first rectangle I drew right here, if I were to revolve that around the x-axis, I'm getting a cylinder that basically, part of it will live below the x-axis. So when I integrate, I'm going to get that volume as well.
The 2 pi takes care of all of those. We've got the r just from what's going up on the y-axis, but then multiplying by 2 pi gets all the rest of the stuff that's revolving around it.
Because
That's
we're
another good way to
calculating
look at it.
that circular area?
Yeah.
Okay. That makes sense.
Good question though.
So what I wrote is going to be
Anybody else? All right, I'm going to stop sharing. A couple things before I let you go. So like I said, test on Friday. Please let me know if you would like to meet or like to discuss anything. There is a quiz today, but since I've already